Welcome to another episode of Chemistry to Your Ears, the podcast from the European Young Chemists Network, or EYCN for short. In this episode, it is our great pleasure to welcome Professor Stefan Grimme, an expert in computational chemistry and density functional theory. Currently a professor at the University of Bonn in Germany, Professor Grimme has made groundbreaking contributions to quantum chemistry, molecular dynamic simulations, and dispersion interactions. His work has significantly improved the accuracy of computational methods and has shaped how chemists model molecular interactions today. Recognized with numerous awards, the most recent one being the 2025 Chemistry Europe Award, his impact on the field is undeniable. In today's episode, we will listen in on our host Konstantina, who will be sitting down with him to explore his research, discuss the future of computational chemistry, and hear his advice for young scientists. Enjoy!
Thank you so very much for joining us today here in the EYCN podcast. So first of all, we would like to take this opportunity to congratulate you on your most recent award, which was the 2025 Chemistry Europe Award. Our most sincere congratulations. We're very honored that you're here today. Our first question would be if you could give us a brief introduction of your work to the listeners who have not had any prior contact to computational chemistry.
I'm a theoretical chemist, so I'm trying to describe molecules and what you can make out of molecules, so liquids maybe even, or solids, just by theoretical means. So we are using the computer basically to describe or simulate what's going on in the real world. So normally in the lab, in a flask, in a solution, maybe in the atmosphere. So we basically build a theoretical or a computational model of reality, and we are looking with some kind of microscope. So the computer is in a way our microscope, and we are going not to the very, very, very fine detail like the theoretical physicists do. So they go inside the nucleus. So basically we stop at the electrons and the nuclei, which define what atoms is. And then we build from atoms, we build molecules, and from molecules we build liquids and solids and so on and so forth. So our duty is to develop these methods that can describe reality to as best as we can. So the word accuracy is important. And then, so we derive these equations, so it's a lot of math. And then we implement these equations into computer programs that basically anybody can use. So one can distinguish our field into method developers and people who mainly apply these methods then to chemical or physical problems. This is a short description.
Great. Thank you very much for your explanations. Based on this, I have two questions. The first one is if there is a difference how systems are treated according to their phase, such as are there any differences between how systems in the solid phase and the liquid phase are treated? And second of all, what are the criteria according to different systems are treated in terms of size, such as smaller systems versus larger systems?
Yeah, first of all, there is not a fundamental difference between the state, so a molecule or a few molecules, and really the condensed phase. In principle, the interactions and the treatment should be the same, because the laws of nature are the same for the electrons in a molecule or the electrons in a metal or in an insulator. The distinction is mainly a technical one, because a solid or a liquid is basically infinitely large for us, okay, while a molecule has a finite size. So, and therefore, this is a technical issue, how to treat these systems of very, very different size. So it's always the problem to scale up our methods from small systems to larger ones. That problem is inherent. We wanna restrict the computational effort. We want to find the right compromise between the accuracy and the comp time we invest in the problem. And Yeah, and finding this right compromise is actually one of the kind of the art in our field.
Mm-hmm.
But there's no fundamental difference between a solid and a liquid or an isolated molecule. It's only in a way, yeah, the systems are more condensed. The atoms are normally closer to each other, but this is no new physics. Yeah, and the second question was what was the second question?
I think they were interconnected if their smaller systems are treated differently compared to larger systems.
Yeah, so we want to basically have something that is seamless, that describes small and medium and large systems basically the same or similar. This is actually one of the problems that we have. We often apply highly accurate methods for small systems, and then we lose basically accuracy and while growing in system size. This is actually a problem. So this is one of the holy grails in a way, to try to make the description as consistent as possible for different sizes. This is an unsolved problem.
Mm-hmm. So you would say that how to treat equally systems of different sizes is a main challenge that exists in the field today. Are there any other challenges that exist in the field of computational chemistry currently?
Yeah, there are a few. So one, in my opinion, what I see is solvation. So a lot of chemistry happens, of course, with a focus on individual molecules, but these molecules are embedded in a solvent. So solution chemistry is normally what is done by most chemists. And so the solvent plays a role, not a very important one, but it is too important to be just neglected. So the model for a molecule in a solvent, like an enzyme in water would be an example, to model this just without the water, say as if it would be in the gas phase, this is a very bad approximation. So we have to develop not only models for the electrons, but also and atoms, but also models for this so-called solvation process. These models are developed, they are reasonable, but I would say currently not really accurate. It's often that the overall accuracy in a simulation, in an application, is actually limited by the accuracy of this solvation problem, for this solvation problem. So, and yeah, this is really a hard one because you have many particles. The solvent, water, you have one molecule that is normally surrounded by hundreds or even thousands of water molecules that are all interacting. So this is often a big system, and big systems are a problem for us. This is one problem I see. This is really challenging. The other one is very complicated electronic structures. I'm just saying here as an example metals. Okay, so metals are intrinsically, so the electronic description, the electronic motion in a way, is complicated in metals. Because basically in metals the electrons are delocalized all over space. And this is for many of the cheap methods that we would like to apply, this is an issue. I mean, in principle, we know how to solve the problem, but we don't know how to solve this efficiently. So whenever we have to deal with true metals, then many of our methods just fail. So the more insulator, the higher the insulator character, the better for us.
I understand.
And this is also, there's no clear way how to solve this. I mean, people are working on it, same for the solvation problem, but not so much progress, say, in the last 10, 20 years or so.
Mm-hmm. I see. So metals and potentially semiconductors are still a challenge in terms of how they should be treated.
In a way, for the experts, say, if the gap between the the occupied and the unoccupied, so virtual states. If this closes, then we are running into problems.
Mhm. I understand. Are there any major breakthroughs in the field since you started working on it? So in the past decades or so?
Yeah, I'm an old guy, so I'm I'm since 30 years in the field. So I did my PhD finished in 91. So yeah, and then I moved to theory. So and the major breakthrough was DFT, so density function theory in chemistry. Of course, it was longer known in physics and already more established in physics. But in the beginning of the 90s of the last century, DFT really became the kind of workhorse in chemistry. And this was also a kind of breakthrough because it enables you to treat systems that were unthinkable before. For example, transition metal catalyzed reaction mechanisms, something like this. That you can only do with DFT and not by the wave function methods that were available in those days. So that was really something totally new. In the mid-90s, really this field exploded due to DFT.
I see. So this approach to treat systems with DFT versus with the other methods is a reason why you were drawn in this field in the first place, or is there a specific reason why you were drawn to the field of computational chemistry?
Yeah, in a way. So I'm very impatient. I wanna have results as quickly as possible. And DFT is the way to go then. It's much faster. So basically it gives a better result in a shorter computation time than any of the wave function theories. Actually, I started my career using Hartree-Fock based methods and wave function theory, but it was kind of not always good enough, and it was painfully slow. And then DFT came in, and you're running the same calculation 10 times faster with a better result in a way. So this was for me absolutely amazing. And then I immediately jumped on that train.
I see, I understand. So basically, Hartree-Fock is a slower method compared to DFT.
Yeah, absolutely. This is just a factor of 10. You get your results in 1 hour instead of half a day.
I see. That's very impressive. Another question that could tie up well with that is the recent rise of AI, if I may call it that. People have been drawn more to theoretical or computational chemistry, with now where computational sciences are more present in the public eye. So my question is, have you seen a drastic impact in your field following this? And do you think that AI could be the successor of DFT in any way?
Yeah, this is a very difficult question because it's a question about the future. I mean, predictions, so true predictions are really difficult, you know. So currently everybody tries AI techniques. So this is an extremely hot field and topic. Right now, it's definitely not competitive to the existing methods. But some of the AI techniques, so say describing the potential energy surface of an atom, of atoms or molecules. So the AI people, they make progress. They have special problems, but I see that there is some potential. If this can replace the existing theories at the end of the day, I don't know. Currently not, but I mean the development goes so fast. So every day there appear new ideas. Maybe in 10 years we will think and talk totally different about it. So I don't know. The AI methods have the problem that they are right now not predictive. I mean, they are only good for what they have been trained on, right? So, but in chemistry, you also need to have some predictive power. The unknown is the interesting. Yeah, and the current AI methods can only work for systems that you know or they were trained on. This is not so a problem in other fields of science, but in chemistry it is, because the unknown is the goal, finding the unknown properties, unknown compounds, unknown reaction mechanisms. And there you need something that is based on a true theory. And this is also the reason why I would always prefer something that is based on a theory, because then you can understand something. And the problem of the AI methods is that you cannot learn anything about it. You get a result that you have, in a way, you have to accept. In theory, with a true theory, you can try to understand that result.
Mm-hmm. I see. So you would say that at the current moment, AI is not as rigid and its accuracy is definitely lower compared to the more robust DFT methods.
Yeah, you can make the accuracy high if you train it specifically on a given system, but then this is limited to this specific system. And then if you outside that regime in another area of chemical space, it may totally fail and you don't know in advance. This is the difficult question. How can we know when it fails and when it works well? And there's currently, people are working on this, but this is a hard problem. Of course, they are much faster than we are.
Mm-hmm. I see. I would like to touch more a bit on to the accuracy of methods, because I know that your expertise into the correlation correction, DFT. How would you describe the DFT world before and after the correlation corrections that you developed?
Yeah, you may call it better dispersion correction, because of course it is correlation, but it is correlation in a specific regime, so when the atoms or electrons are relatively far from each other. So the main effect of dispersion, or this long-range correlation, that would be another name, is when the system is large. So you can't see it for small systems. So just small molecules show little dispersion or correlation effects of this kind, simply because the distances between the electrons are not big. They are all small, and then there is only a small contribution. And therefore, the importance of this effect has been overlooked for decades, because people were limited just by the computers and by the software to investigate small systems. But then in the 90s, with the advent of DFT, people more and more looked into much larger molecules. So molecules with not, say, 10 atoms, or maybe 50 or 100. And then you see immediately, if you carefully look into your results, that there are systematic errors. Systematic errors that increase with increasing size of the system. Yes, you simply miss some physics. Yeah, and that has been, say, noted by some people already in the mid and end 90s, but basically no solution was suggested. That problem was noted, a few experts were aware of it, but it was kind of hidden under the carpet. So just let's forget it, okay? So everybody was happy with DFT, and yeah. And then this problem showed up more often and really seriously also in qualitative failures. So some of the DFT calculations were qualitatively wrong for some systems. And then, so the best example are these non-covalent interactions. So the interactions are weak, but you have very many of them, and therefore systems form solids and liquids. So, and if you would just neglect these interactions, these long-range correlations, then it would just be a gas instead of a liquid, which is totally qualitatively completely wrong. And then some people, including me, proposed corrections for this, to cure this problem. And they are computationally relatively simple, theoretically well-founded, and then over the years and decades, this became a standard in the field to do these dispersion corrections. Still, they are ignored or not included by some people, but I would say that the majority of computational chemists use them nowadays. And that was a big step forward because then DFT, in a way, is consistent and applicable to basically anything.
I see. In that sense, when using your method, has any collaboration in your field of application surprised you? So is there a collaboration that does use your methods, but you have found particularly interesting, cited in the literature or so?
Yeah, what comes to my mind here is a collaboration that I had some years ago with Peter Schneider from Gießen, who is an organic chemist. And he came up with the idea of investigating textbook examples for organic molecules which are not stable by so-called steric interactions. So chemists often argue with the sterics, so a molecule is stable or unstable because there's because functional groups come spatially close and there's then too much repulsion pushing the energy up. And so they cannot be made. So synthetically, there's often this steric argumentation. And he came up with the idea of molecules where when you increase the steric demands, if you introduce more functional groups which have repulsion or increase the repulsion in your molecule, then these molecules became actually not unstable but stable, so they can synthetically be made. The example was hexaphenylethane, which is not known, this molecule. It basically spontaneously dissociates. And if you put now on the phenyl groups tertiary-butyl groups, which are thought to be sterically demanding, then actually this molecule became stable. So you can synthetically make it. And so I analyzed this then, and the reason is this dispersion, so the long-range correlation, which was a surprise. So we, in a way, completely have to change our mind, not completely, we have to change our thinking about these steric interactions. So if these functional groups are oriented properly, then their interactions can be attractive instead of repulsive, which is changing the view. And this is so clear. That was really for me a surprise, and I'm really acknowledge this collaboration because you need somebody who knows organic chemistry well and all the textbook examples that are given. Yeah?
No, this is a really impressive example how the computational chemistry can collaborate with the more experimental chemistry and how both methods can complement each other. Would you say that this is a widely spread phenomenon of computational chemistry being complemented by experimental data?
Yeah, nowadays this is quite common. So this is, you see in an increasing number of papers where computations augment some experiments. This is now, I would say, maybe 20, 30, even 50% of the high-level journals, the papers, if you're checking, then you will find some computations. Maybe not dominantly, but part of it. And that was totally different maybe 20 years ago. 20 years ago or 30 years ago, it was absolutely rare that there is a close collaboration of theory and experiment. I mean, it's also the result of the software development. Nowadays, everybody can use quantum chemical software. It's easy to use. Yeah, why not?
So it was rare a few decades ago to be such a close collaboration between computation and experiment. Why is that? Apart from the software issue, is there another reason or?
Yeah, it is generally that the borders between the disciplines were stronger. So that there's inorganic and organic and physical chemistry and then additionally theoretical chemistry. This is nowadays mixed up a lot. So. And this is good that it is so. People are talking to each other. People are using more frequently other tools or methods just as tools to solve their problems. In the old days, it was you belonged to a school of whatever, you were a spectroscopist or an inorganic chemist, and then you were trapped in your field without looking to others.
I see. I also think it's very good that now the borders between disciplines have been eliminated. I have a question regarding this. You said that the borders between different academic disciplines have now been erased in a way. How would you describe the borders between academia and industry? So, for example, are people working in the industry familiar with how well your academic research, so computational chemistry, can translate into industrial applications?
I think this is a kind of diffusion process. It always takes time until methods are really accepted. So first they have to be accepted in the academia, and then they diffuse into the industry. This takes decades, I would say, but I think people now really see the potential because, I mean, in industry, it's clear you have to save money, right, in your development. And then you see that theory is good, it's robust, and it's extremely efficient. You can investigate things that are extremely difficult, if not impossible, experimentally, and it is quick. We are fast, right? We can solve problems in days or in a few days. And this advantage that we are cheap, economically very, very reasonable, that this idea now spreads out, and so all the big companies have large theory groups partially. In Germany, it's mainly the BASF. So they have long-standing collaborations with theory, but also other chemical companies, and of course also the pharmaceutical ones. This is changing, slowly changing, but it's changing.
No, that's very impressive. I was not aware of that, and I think our listeners were not aware of that. I have also a question in terms of, let's say, students who would like to get to work into the field of computational chemistry. So, interested students, which are their coding skills or their background that, let's say, a bachelor student should have nowadays in case they would like to do research in your field or to work in your lab?
Yeah, generally I would say one should be interested in math and computers. But detailed knowledge, I think it's not required. I would always would favor the approach of learning by doing. I mean, it's not necessary that you know Python or C or Fortran or whatever. That is something that you learn. But you should be open-minded and open to think in a special way, I would say in an analytical, fundamental, physics, math theory oriented way, right? So the general setup of your mind should be in our direction, but there is no need for any special knowledge or whatever. You have to be open to and interested, and broadly interested, I would say. You should be interested in knowing why something works or does not work, right? So this is it's a bit maybe a question of character, personality.
So you would argue that intuition and motivation is more necessary for a student who would like to work in your field rather than pre-existing skills that one learns during their studies.
If you are highly motivated, then you can learn in half a year basically anything in the fundamentals in our field. So programming, simple programming, and the basic theory. This is absolutely doable.
No, this is very interesting because I feel like in this way, people who are indeed interested in the field will not have probably any difficulty into working in this field, even in different.
Yeah, absolutely. Yeah, I would agree.
That's very interesting. Thank you. So another question, maybe reaching towards the end. Are there any fundamental problems and unsolved questions in the field of theoretical chemistry that you hope to see solved someday?
Yeah, this is why I'm related to what I already said. So this solvation and I call it, let me call it strong correlation. So the metals. So we are more going to the solvation problem. So we're trying to solve the problem how to automatically treat these systems with very many molecular degrees of freedom. So if the molecules are flexible or many molecules come together, say if you're forming basically a liquid from small clusters or aggregates, then the number of degrees of freedom, so the flexibility increases. And how to treat this is one of our more concrete problems. So in workflows. So we want to develop something that is automatic. So you have a problem and you, in a way, simplify, you press just a button and then at an hour or a day or a week later you get a reliable answer. And we call this a workflow or automatic workflows. And the complexity of these workflows depend then on the problem. So is it a spectroscopic problem or a chemical reaction or and making this automatic and robust and stable, this is one of our goals. So then everything comes together. So the software, the methods, also the hardware in a way. You need big computers, but how? Graphic cards or CPUs or parallel supercomputers, whatever. Yeah, it's also of course software development. So, but you need also chemical knowledge and chemical intuition. So it's absolutely interdisciplinary to work on such practical problems. So as an example, maybe what we are trying to do right now, or since 10 years already, is computing mass spectra. So mass spectrometry is absolutely important in chemistry. Every chemical lab has a mass spectrometer. This is extremely important for analytical chemistry. You need to know what is going on in your flask. And mass spectrometry is a standard tool which was also ignored for many years by quantum chemists. So, and we are trying to make automatic workflows to predict mass spectra. And at the end of the day, it's the identification of unknown compounds. This is the ultimate goal. No? In analytical chemistry, you get some signals in a HPLC and after measuring a mass spectrum, and then you want to know what it is. So what is this peak, to what molecules is it related, or what molecule? And doing this automatically, annotation of spectra by molecular structures, this is one of the kind of holy grails in analytical chemistry. And we're trying to contribute to that really tough problem.
I see. Towards the automated workflows that you just described, do you think that any upcoming or current developments in a field related to yours, such as, let's say, quantum computing, could be beneficial?
Yeah, I mean, the problem that I just described is something where already AI people are hard working on. The quantum computing is a bit different story because in order to be applicable, so quantum computing is really nicely applicable only to problems which are inherently quantum in nature. So the electronic structure problem of a metal, for example, is something that nicely can be computed on a quantum computer if you have enough qubits. But the many other degrees of freedom that we have to treat for what I just described, say mass spectrometry or a liquid, are not quantum but are classical degrees of freedom. And for the classical degrees of freedom, the quantum computer doesn't help. So I see some potential of quantum computing in chemistry, but not so much, maybe less than in other disciplines. So the classical computer, I think, will be still absolutely dominating in chemistry, maybe even in 20, 30 years or so. Because our problems are often semi-classical or not fully quantum. For the electronic structure problem, you can use the quantum computer nicely, but not for sampling the conformers of a drug. There it's useless, because this is a classical problem. Not many chemical problems are truly quantum. But this is, of course, my personal opinion. My colleagues who are working in the field of quantum computing will obviously think different about it. But this is my practical point of view.
Mhm, mhm. So in the automated workflows that are relevant to, let's say, predict the mass spectra of molecules, which is an advancement that could be beneficial towards this direction?
Yeah, this is because you have very, very many fragmentation pathways. You have to run a really huge number of computations already for relatively small molecules. So you need very fast methods. And this is where we are really working on in the last 5 to 10 years, developing approximations to DFT. So DFT basically made 100 or 1,000 times faster. This is what I'm actually working right now on. So so-called tight binding methods. They are a bit worse than DFT, but much faster. And in this way, we can try to run such for example, mass spectrometry calculations, say, on a laptop, without any need for a supercomputer. So anybody then can do it.
This sounds like a very impressive advance on the field that I believe all chemists would be very excited for.
Yeah, we are not fully there, but we are on a way, I think, on a good way.
That's great to hear. Thank you very much for your time. I think those are all the questions I would like to discuss.
Yeah, many thanks for inviting me.
Would you have any closing remarks or that you would like to say to our listeners?
Go to science, do science. Science is something nice to do. It's a good feeling. You satisfy yourself, but you can also help the world to be a better place. So it's a nice thing to do. I'm doing it since more than 30 years, and I will do it the rest of my life. And I'm so happy with it. And this is the only thing I can say. And you also can earn some money with it. Not too much. Money is not so important. But it can be a nice way of living, in my opinion.
Thank you very much for your kind advice to us and to our listeners. I think we will take your words in heart. And thank you also very much for your time and your insights into the field. It was really a pleasure and an honor to hear from an expert, well-established expert and very highly cited chemist. So thank you.
What nice words to end this remarkable episode with. Once again, a huge thank you to Professor Grimme for sharing his insights with us today. And of course, a big thank you to Konstantina for hosting this fascinating discussion as well. We hope you enjoyed this episode of Chemistry to Your Ears, and maybe this has even sparked your interest in starting your own career in computational chemistry. If you enjoyed the episode, feel free to share it and follow us for more exciting episodes around all things chemistry. Until next time.